So last video lecture, we looked at how to represent motion on position versus time graphs, like the one shown up here. Today we're going to build on that and discuss two distinct types of motion, and then we're going to actually introduce calculus to get more details of how we describe motion at a finer sort of level. So if you recall, we had sort of established that on a position versus time graph, the slope of that graph represented the average velocity between the 2 points. So shown on this plot here is a bunch of position measurements in time that actually have a constant slope. That object's moving at the same speed or the same velocity over the entire time interval shown. Now this in this case, the average velocity is actually the instantaneous velocity. The speed's not changing. So if you take the average of a constant value, you get that constant value. We have one velocity for the whole thing. This is a special type of motion we call uniform motion. The reason we kind of care about uniform motion and give it its own name won't be obvious until we get to Newton's laws in the next section of the course. But for now, just acknowledge that uniform motion is defined as objects with uniform motion have a constant velocity, same speed, same direction, and they're not changing. And in this case, if you're in uniform motion, your average velocity is the same as your instantaneous velocity, and it's the slope of that position versus time graph. If we are in uniform velocity like this, we can actually use the same sort of calculation we've been doing, change in position over change in time to get our average velocity, but we can also flip that. If we know we're in uniform motion, and I write that average velocity as x final minus x initial, just that change in position over some change in time interval, if I know that I'm in uniform motion and have some velocity, I can rearrange this equation to give me v delta t is equal to x final minus x initial, or doing a little more algebra, x final is equal to x initial plus v delta t. And this is actually pretty useful. If I know where I started, what my initial position is, and I know I'm at some constant uniform velocity, then I can predict where what my position will be at some later time just by taking this equation and plugging in the time until then. So anyway, the point is, some of the takeaways from this is recapping that our velocity on a position versus time graph is the slope, and the way we've been calculating it is the average velocity between 2 points or over some time interval is the slope of that line on the position versus time plot. And if we have a constant slope, or our position versus time graph is a straight line, we are describing what's called uniform motion. So if uniform motion is constant velocity and a straight line on a position versus time graph, non-uniform motion is non-constant velocity and a curved line on a position versus time graph. So let's imagine some object moving with the following position versus time graph. We've measured its position at every second as it travels, and we see that it is, if we were to draw the slopes or look at the average velocities in each 1 second time interval, we would see that the slopes are slowly increasing. Now, if I were to ask you to say, tell me what the velocity was at 3.2 seconds, what would you say? There's a few ways we might come about and try to think of this, but with the, data points we've taken, we're not going to be able to get an exact velocity at that point, right? One of the things we could do is take the average velocity between those 2 points, so just take the slope of between the point at 4 seconds and 3 seconds, and calculate that slope and say, well, that's the average velocity between 3 and 4 seconds. So at 3.2 seconds, it's a pretty decent number to assign for that velocity. But that's not exactly going to be the same velocity. If you look at, if you kind of with your eyes draw a smooth line that's connecting these, you imagine it's going to, hopefully you can kind of draw a smoother line than I can, but this sort of curved line that goes up, and the slope between 3 and 4 seconds that we calculated as our average speed is not going to be the same as the slope at that 3.2 seconds. It's going to be a little off. So what do we need to do? Well, this is where calculus comes in, right? We've been calculating our velocity as v is equal to delta x over delta t. This was our average velocity. And when we have certain points like this that are shown here on the plot, if we wanted the velocity at t2, we could take the average velocity of 2 points surrounding that and say that's it. Use that as our velocity. But the further apart those points are, the more likely they're going to come up with, they're going to be slightly off the instantaneous velocity. If we zoom in and get more and more data points and slowly make delta t smaller, we're going to get more and more accurate and a better approximation of the velocity at that instant. And ultimately, this is where calculus comes in. The instantaneous velocity at any time is essentially the limit of delta t going to 0 of delta x over delta t is going to be our instantaneous velocity. And that's just extremely useful, because now if we're given, jumped ahead of myself there, if we know the position as a function of time, we can get the velocity at any instant on that is just going to be the derivative of that position as a function of time. Hopefully you remember back, calculus is a prereq, that's essentially what derivatives are. And on a position versus time graph, the instantaneous velocity is the slope of that function at a given time. So we're going to use that through this course. I'm not going to spend a lot of lecture time. None of this video is really going to go through this. Calculus is a prerequisite for this course, so I'm going to assume you've all seen this and are familiar with it. If you are struggling, though, feel free to reach out to me. We can discuss it in an office hour or another session or something. But for now, all the rules for derivatives that we know, how to take derivatives, chain rule, derivatives of a constant or zero, we're just going to use those. And if we're given, again, the position as a function of time, we can get the velocity by simply taking that derivative. We've just shown, or we've kind of discussed how velocity is you can get from the derivative of the position with respect to time. And that gives us the instantaneous velocity at any time. What about going the opposite way? What if we wanted the position somehow if we were given the velocity? How would we do that? Well, let's think back to the earlier discussion we had about uniform motion. So in uniform motion, we had position versus time plots that look something like this, right? Position versus time plots that had some straight line, right? And if we wanted to know from some t0 to some later t final, the position at those 2 points, x initial or x0, and then x final, we knew that we showed that the final position was just the initial position plus the velocity times that change in time interval. And this worked because the velocity was constant. This was uniform motion, same velocity, same speed, same direction. Position versus time graph has a constant slope. So this is essentially just using that slope to calculate a spot further on that line. But that's not going to work for non-uniform motion, right? In non-uniform motion, we have something that looks more like this. We have, our position as a function of time is just going to have some shape to it, right? It's not a constant it's not a straight line. It's non-uniform motion. So if we wanted to go from some t0 to some t final and figure out what the corresponding x0 and the corresponding x final would be, we're going to have to do something else. We can't use this equation that worked for uniform motion because that velocity is changing. But what we can do is we can break this whole trip from this initial position to this one into a bunch of very tiny steps, right? So if I go to some intermediate step, we'll call this T1, and I want to know how far that X1 is. Well, this line is, if I zoom in enough, is essentially straight, right? So what I could say with that is that x1 is going to be equal to x0 plus v1 delta t, where v1 is just the slope between those two lines, right? And then if I wanted to take another very small step to t2, well, I would just say, okay, well, x2 is going to be equal to x1 plus v2 times delta t, where I've taken some other small step in time and I've gone from x1 now to x2, and that slope between those 2 points, v2, is essentially constant. And I can keep doing this. One of the other things I can do is I know what x1 equals. So this x2 is actually equal to x0 plus v1 delta t. That equation is for x1 substituted in there, plus v2 delta t. Then I take another small step of delta t, and I get x3 is going to be equal to x2 plus v3 delta t, where v3 is going to be that slope between the next small step. I can then substitute this equation in for x2, and I get x3 is equal to x0 plus v1 delta t plus v2 delta t plus v3 delta t. And you can see how I can keep doing this all the way along until I've made it all the way to my final time, right? And then I'm going to get x final is going to be equal to x0 plus v1 delta t plus ... all the way up to we'll call it final delta t. Or written more compactly, x0 plus the sum of I of all those different velocities times that delta t is how I get to my x final. So basically, I use the same thing we thought about for uniform motion when we had a constant velocity, but rather than looking at the whole trip, I break it down into a bunch of small steps where I can essentially say, if I'm looking at a small enough time, that velocity is constant for that time interval. And that's essentially what we do. When we take that limit of delta t goes to 0, this all becomes x at some time later is equal to my initial x, or what we've called x0. That sum becomes an integral of the velocity with respect to time from my initial time to my final time, right? And this is how, if we know the velocity as a function of time here, we can just integrate it out and get the position at some later time. So again, we're going to calculus this way. We can get position as a function of time. If we have that, we can just simply take the derivative of it to get velocity as a function of time. dx dt gives us that velocity. If I know the velocity is a function of time, I can go the other way, and my change in position, right, my x t minus my initial x is just going to be equal to that integral of my velocity with respect to time from t0 to t final. So this delta x is the integral of that velocity with respect to time. So we can go back and forth just using calculus, instantaneous position or velocities from position as a function of time and changes in position given a velocity by taking the integral. Another thing we want to realize is what we're actually calculating. You probably were told at some point in your calculus class how this integral is represented graphically. So hopefully in your calculus classes, you were taught that integrals are essentially areas under the curve. So if we go back, for the straightforward, or I guess more straightforward example of uniform motion, if we have our velocity as a function of time plotted, again, it's a straight line. Oh, sorry, uniform motion. It is a flat line. That velocity is constant, right? And when we looked at t initial and t final, and we wanted to calculate that position, we had x final was equal to x initial plus that velocity times delta t, or x final minus x initial, which is just our change in position, was equal to velocity times delta t. Well, velocity that's our v. It's the height of this square. Delta t is our delta t here. So our change in position was the area under the curve. In the non-uniform motion, where we have the velocity as a function of time that has some slope to it or some changing, it doesn't even have to be constant, it can do whatever. If we want to go from some t initial to t final, what we've just the equations in that we've just derived here, this change in position here, that integral part of it is just the area under the curve gives us that displacement or change in position. So we've got calculus, moving back to what we just showed, we've got the derivative takes us from position to velocity. The integral goes back the other way and takes us from a known velocity to a displacement or a change in position. And then graphically, way down here, if we have a velocity versus time graph, the displacement or change in position is just the area under that curve. And as we've discussed in previous lectures and earlier in this one, if we have position versus time, the velocity is the slope of that graph at whatever point we're looking at. This brings up sort of a very important point. You have to pay attention to the axes of what is given. A position versus time graph or a velocity versus time graph all mean different things. Be sure that when you're trying to think about what's plotted, you're paying attention to what those axes are labeled as, because they mean very different things. Always label your axes. Anyway, with that, we're going to use sort of all the pictures that we've been building up on, visual representations, graphical representations, the mathematical representation we developed today with calculus. And next lecture, we're going to use those to derive the kinematic equations for constant acceleration. This is sort of the core of our mathematical picture and what we're going to use to reason through quantitative problems to solve a lot of the things in this course.